Assalamualaikum, my name is Nik Muhammad Alif Irfan bin Azhar. Today I will present about the triple integral in spherical coordinates for the introduction and sample question. Spherical coordinates represent a point in space by ordered triples of P, phase and theta, in which P is the distance from P to origin that we can show from this. For the phase is the angle between the positive z-axis and the line from the origin to the point P that we can show from this. And lastly, for the theta is the angle from cylindrical coordinate, also we can show from this. For the relationship between a point P, S, Y, Z in rectangular coordinates and equivalent point P, P, phase theta in spherical coordinates as S equals to P sin phase cos theta, Y equals to P sin phase sin theta, Z equals to P cos phase, R equals to P sin phase, and P square equals to X square plus Y square plus Z square, with the restriction on the coordinates P the larger or equals to 0 and the value of phase is from 0 to pi. This is for the simple equation of triple integral. Evaluate the triple integral of tan xz plus 3 dB, where E is the region portion of x square plus y square plus z square equals to 16, with z equals or larger than 0. This is for the general equation. For the coordination, this is for the coordination that we get from this graph. This graph we use the symbol lab software, and for the value of s is equals to P sin phase cos theta, and the value of z equals to P cos phase. Substitute the value of z to the general this general equation, and we get this equation. Firstly, do the first integral over the dp first, and then we get this equation. Then substitute the value of 4 and 0. Then do the second integral, which integrate over the theta, and then we get this equation, and substitute the value of theta with the 2 pi and 0. Then for the last integral, we integrate to the phase, and we get the final answer is 128 pi. Finally, we run and use the software by using the software symbol lab to confirm the answer for the equation that I already explained before.
Hi everyone, I am Nur Arifkan, and I'm gonna talk about Stokes theorem. Stokes theorem can be drawn as a higher dimension version when we have a closed curve in 3 dimensions, when the curve is the boundary of the surface S. We assume that the curve is positively oriented, which means the part of the curve going to the counterclockwise direction with respect to the normal vector of the surface. Now, if we have the vector field permanently spaced to find the amount of the field that goes to the direction of the curve, we would need to take the line integral of f along C. Stokes theorem gives another method of finding this line integral, which can lead to the simple calculation. The theorem states that the line integral of the f along C is equal to the surface integral of the curve of n dot n over the surface S. Remember that the curve of the vector field is calculated by taking del cross f, where del was the vector, d by dx, d by dy, and d by dz. While we can use Stokes theorem to calculate the line integral, it can also be used in reverse if we want to find the surface integral of a curve. and the boundary is simple enough to calculate. Now, let's see some example of Stokes theorem. Let's go!
Assalamualaikum and hi, my name is Muhammad Azri bin Ahmad Fauzi. My metric number is B0120100147 and I came from group 7. So today I will present some example question for Stokes theorem. So for the first question, we need to verify Stokes theorem where S is the lower hemisphere, Z is lower than 0 of the radius 3, is oriented with the downward normal, and for the equation we can see on this question. So let's see how to solve this question. To solving this question, first we change it to a parametric equation. Then the range is 0 to 2 pi. We change x equal to 3 cos t. We differentiate it and it becomes negative 3 sin t dt. Then we differentiate y equal to 3 sin t. Then it will become 3 cos t dt. So now we insert the value into the formula and do a integral. Finally, we will get the answer negative 9 pi.
Assalamualaikum warahmatullahi wabarakatuh. So my name is Akif Asnawi bin Takroni and my metric number is B0120108008. So now after we have known all about the Stokes theorem, then I will talk about the function and application Stokes theorem, especially in electrical engineering field. So now firstly, Stokes theorem function is used to transform a difficult surface integral into an easier line integral or vice versa. Which through Stokes theorem, line integral can be evaluated using the simplest surface with boundaries. Second, to find the line integral of some particular curve or spherical coordinate, which is when I want to find the line of the particular curve, I can directly use the Stokes theorem. Third one is determine the curl of a bounded surface, and the fourth is the sweeping surface, which since Stokes theorem say that if we want to evaluate the circulation along a surface, we need only look at the boundaries and we can swap one surface for another, provided that they have the same boundary. Okay, so now we move to the application of the Stokes theorem in electrical engineering field. So the first one is a derivation of Faraday law. Faraday law relates the curl of electrical field to the rate of change of the corresponding magnetic field. It can be used to derive Faraday law. And we notice that the curl of the electrical field doesn't change over time, although the magnetic field doesn't change over time. And in context of electrical field, the curl of electrical field can be interpreted as the negative of the rate of the change of the corresponding magnetic field with respect to the time. And this is the derivation of the Faraday law. Okay, so next is the fluid mechanics, such as in a whirlpool motion or another. And in every point of a curl of the vector field is represented by the vector where the certain attribute of this vector, such as magnitude and direction, give us idea of the rotation of this vector field about some point. The double integral gives us the total amount of curl or twist with respect to the boundary region. So that's all from me. Thank you.